So, good morning, everyone. I'm Belinda Damian. I'm a postdoc working at St Andrews with Alex Scholz. Before I begin, I'd like to thank the organizers for the opportunity to present my work today, which also gives me an excuse to escape the Scottish winters for a few days, which is great. So this talk will be a continuation on what Ray presented yesterday, where he talked about the result for one particular object where we saw an interesting accretion burst. So today I'll be talking about the complete sample of planetary mass objects that we observed with JWST. So I should give due credit before I begin to Alex, Ray, and Cora, who are the PIs of this program. I was just lucky to work with this amazing data set along with the rest of our team. So let's talk about disks around planetary mass objects, which is the theme of this session. So we know the protoplanetary disks are an important byproduct of the star formation process, and I don't have to stress on how important it is in studying planet formation because we've been talking a lot about that in the past 2 days. But it's been well established over the last 2 decades or so that just like stars and brown dwarfs, planetary mass objects also have a disk around them. But the primary evidence for that has come from infrared photometric studies, mainly from the mid-infrared X's that we see above the photospheric fluxes. But since these objects are intrinsically very faint, it's been a challenge to characterize in detail the disk around these objects with spectroscopy. And we know from Ray's talk and Matthew and a lot of others who spoke yesterday how important it is to obtain the spectra for these objects. But at the same time, it is time intensive and it's very difficult as we go to lower and lower mass objects. So given the lack of spectra for the disks around these objects, it has raised a lot of questions. Most importantly, if the disk around these objects can host their own planetary ecosystem. So our program was designed to address this very question by looking for potential disks around planetary mass objects. So for this work, our sample was meticulously handpicked again by Alex, so I should give him credit for that. So he picked 8 planetary mass objects belonging to 3 different star-forming regions in Taurus, Chameleon 1, and Rho Ophiuchus regions. So they are pretty young, a few million years old. And one important characteristic feature that he looked for was all of them had mid-infrared X's based on their Spitzer-Iraq photometry, which is sort of a signpost to say that there is a disk around these objects. So this is the color magnitude diagram, which Ray already showed yesterday. So at the bottom, I have marked our planetary mass objects there. And based off their K-band absolute magnitude for a 2 million year age, their mass would be somewhere around or below 10 Jupiter mass. And also their K minus 4.5 micron color, if you see, is more enhanced compared to the photospheric color, which is again an indicator to say that these objects have a disk surrounding them. But does that mean that all of these objects really have a disk around them? And even if they do, then the bigger question is, can these disks have their own planets or moons or satellites, however you want to call them? So to answer that question, yes, we need to look at their spectra. So now enters JWST. So for all the 8 objects, we obtained low resolution spectra from between 1 to 13 micron with 2 instruments on board JWST. One was with NIRSPEC in PRISM mode, and the other was with MIRI in LRS mode. And this was taken as part of the cycle 3 observations. And this is a very nice plot which comprehensively illustrates the complete data set that we have. So in green is the shorter NIRSPEC data, and then in orange is the MIRI data for all the objects, and it's stacked in increasing order of their spectral type. So there are a lot of similarities as well as certain differences that we see in the spectral features among the 8 objects here, which I will talk about. But before that, I just wanted to briefly show you how far we have come along with JWST, just to take a minute to appreciate the sort of data set that we now have. So on the left is the SED of a planetary mass object called OTS-44. It's in the Chameleon 1 star forming region. It's an M9 spectral type object. And overlaid on the SED is the mid-infrared spectra for this object. And this was taken almost or more than a decade ago with the Spitzer IRS instrument. And you can see how low the signal to noise ratio is. Before JWST came into existence, this was the only mid-infrared spectra that was available for a planetary mass object. And now with JWST on the right is the spectra for a similar spectral type object that we have observed. And although both of them are low resolution data, you can clearly see the drastic improvement in the quality of the spectra with JWST. In fact, we can see the 10 micron silicate emission feature here with the MIRI data, which was great to see and to work with. But I just wanted to highlight that. So coming back to the analysis, so the first step in this sort of study is to quantify the photospheric properties, obviously. So estimating their temperature, spectral type, extinction, etc. And we've used pretty much standard techniques to do that here. So I'm not going to the details of it, but this plot here is a sample for one of the objects that we observed and how we get the spectral type by comparing the NIRSPEC data with standard templates. So the blue spectra here is the best match for this particular object. And the other four colored lines below that just show the uncertainty range in spectral type and extinction. So for the 8 objects, the spectral type came out to be M9.5 to L4, which sort of matched with the previous literature estimates. And similarly, to get the temperature, we again compared the shorter wavelength NIRSPEC data with photospheric models. Here I've used the BT settle model. And so each panel is for each of our targets, and in black is the best fit photospheric model for each of them. So from this plot, we can clearly see that for 6 out of the 8 objects, so that's excluding this one, the second one here, and the last one here. So excluding those 2 objects, the other 6 objects clearly have a mid-infrared axis above the photospheric fluxes. So this is just a zoom in on one of the objects where you can clearly see the axis. So the best explanation for that is the emission from the warm dust in the disk. So that clearly demonstrates that these planetary mass objects really have a disk around them, and that's the spectroscopic evidence for that. So coming to the photospheric spectral features, so I've just taken 2 objects from our sample just as a representative sample of the spectral type range that we have, and then compared it with 2 well-studied similar spectral type objects from literature, not similar spectral type, but similar type objects, and put them together here. So here, the first thing that we obviously see is the prominent water absorption features that are present in all of our planetary mass objects. And as Ray was mentioning yesterday, the depth of the water absorption feature increases as we go down to cooler and cooler objects. And secondly, we also found, not for all of the objects, but some of them had this absorption dip at 4.3 micron and another absorption dip here at 3 micron, which we initially thought was associated with the atmosphere of the object, but it happened to be water ice and CO2 emission from the molecular cloud instead, because only objects which had higher reddening showed the absorption features. It's not present in all of them. But one important point that I wanted to emphasize here is, on the whole, what we have seen is the atmospheric models don't really work well for the complete photospheric wavelength range from 1 to 5 micron. So that is something I'm currently looking at. So I just thought I'll throw this figure there. So this is one of the objects which does not have a disk around it, which is in black here. And then I've tried 3 different photospheric model families to find the best match for it. And this was done just for the shorter wavelength up to 2.5 micron. And you can clearly see that it doesn't really work, especially in the 3 to 5 micron range. It doesn't do a good job in constraining it. So if anybody has any ideas or suggestions how to tackle this, I'd love to discuss more on this, but I just wanted to highlight this here. Coming to one of the important results from our work. So with the MIRI mid-infrared data for the 6 objects which had a disk around it, we saw this 10 micron emission feature from the silicates. So these silicates are an important component of dust in the disk, and it's been shown that silicates are present in the disk around stars and brown dwarfs. But this is the very first time we are seeing silicates in the disk around a planetary mass object. And not just in stars and brown dwarf, silicates are also present in the ISM dust and even in comets. So this plot here is from API 2005. That was the first study that reported silicates in the disk around brown dwarfs. So they give a nice figure which compares the emission feature for brown dwarfs with the ISM dust as well as with the Halley-Bopp comet, where you can see for the ISM dust, it's more of a narrow single peak, but that's because of the amorphous silicates. But when you come down to the comet, which has more processed crystalline silicates, you can see a double peak, which sort of gives a plateau-like structure. So I did a similar plot for our 6 objects which have a disk around it, and that's this one here. And we do see a diversity in both the shape and the strength of the silicate emission feature among our 6 objects. And in this plot here, I've just compared the 6 objects with their higher mass counterparts, like brown dwarfs, T-Tauri stars, and Herbig A-B stars. So the x-axis here is just an indicator of the grain growth, and the y-axis shows the degree of crystallization. And you can see that the planetary mass objects occupy a space that's similar to brown dwarfs. So some of them have show an evidence for dust processing and grain growth in the disk around them. So that's sort of the first step towards forming planetesimals. So it's an evidence to say that, yes, the disk around planetary mass objects can, in fact, have their own rocky companions. And for the other 2 objects which did not have a disk around it, we just wanted to see if we could find silicate absorption feature from the atmosphere, because it's been reported previously in much older brown dwarfs that there's an absorption feature at around 10 micron there, which is due to the silicate clouds that are present in the atmosphere. So we just wanted to check that for these 2 objects. So we measured the silicate index and then compared it with their respective spectral types with much older brown dwarfs. And only one of the 2 objects has a weak silicate index here, and it's still lower than the median value that we get for the older brown dwarfs. But of course, this is just one sample that we have now. We do really need a larger sample. And I know that's a luxury that sometimes we cannot afford, but we do need a larger sample to, in fact, see what sort of relation there is between the absorption feature and, say, the surface gravity and, in turn, the age of the object. And before I finish, I just wanted to highlight one other important result from our team. So this work was led by Laura Flagg, which was on the same object which Ray presented yesterday in the Chameleon region. So for this object in the MIRI data, we did see 2 hydrocarbon emission features at 7.7 and 10.5 micron. That's due to methane and ethylene. These features are also present in a few more of our planetary mass objects in a sample, but this is the one which shows the significant feature. And so this makes them the lowest mass objects ever detected with hydrocarbons in the disk around planetary mass objects. And she also compared the spectra for this object with a higher mass star. This is a T-Tauri star here. And so the black one is the spectra of our planetary mass object, and in blue is the spectra of the star, and in light blue is the best fit photospheric model for this object. And just by scaling it by a constant, she could find almost a perfect match with the star there. So this sort of tells us that the inner disk conditions are kind of similar across a wider mass range than what we had initially thought, because the comparative object here has a very rich carbon-rich chemistry for the disk. So this similarity tells us that the inner disk conditions could be similar from stars to brown dwarfs and even planetary mass objects. So yeah, with that, I will leave the summary slide up, and thank you for your attention. I can take questions.
This is really interesting. So I want to ask, what is the mass of your warm dusty disk compared to your object? What is the ratio?
We don't have an estimate for the mass as of now, so maybe a few Earth masses, I'm guessing, if we have to get the ratio from the central mass of the central object and compare it with the disk. I'm guessing a few Earth masses because these are like 10 to 15 Jupiter mass objects, but I don't have an exact estimate for the disk mass.
Yeah, hi. Very interesting. I was wondering, to form crystalline silicates, I think you need a temperature of about 1800 Kelvin. So, and those objects more or less have that temperature. So do you have any idea on how you can get those crystalline silicates in those disks of around very, very cool objects?
So if I understand your question correctly, you're asking about the disk temperature?
Right, yes. In general, how you expect to form the crystalline silicate. For me, it's fascinating around such cool objects.
So for this particular object, which Laura worked on, she did some LT slab modeling to get the inner disk temperature. So that was around 100 to 200 Kelvin, I think, which she got. So that's just for one object that we did. We haven't done it for the rest of the sample.
Question here. So these carbon-rich disks, right, around these colder or these low mass objects, that's kind of one of this. It seems like that's like a really big finding that's not getting enough play out of JWST, that they're really carbon rich, which is also seems like what you're saying here. What does that mean for the evolution of an object that might form around them? So a planet that they might form when they're like uber carboned.
Okay. So that is true that it's not fully explored yet, what you mentioned first, because although if I can go back to this figure here. So there's traces of that feature that we see in few of the objects, but not as significant as this one. So we can't really tell if it's a common feature that we see in planetary mass objects with disk, or this just happened to be one. We don't know. But with this, what we see is, again, only a few of them have signatures of, dust processing and crystallization, because the other three here have a single peak, which is more related to the amorphous silicates like the ISM cloud. They're more primitive in nature. But all I can say is this is a very limited sample right now to give a more generalized comment on that.
There's a couple other people coming out with this result too, though. This is like a thing, right?
I don't think it's, yeah.
Hydrocarbons is one thing, but then these carbon-rich disks. So that's, you can get the hydrocarbons, but now this big JWST finding, carbon-rich disks around these brown dwarfs and proto-brown dwarfs, and then, okay, we can talk about this later, but I actually think this is a huge deal that we should all talk about as a free-floating planetary object that might form, get ejected, and then we get carbon-rich crazy objects. Speculation, people.
Then I think we can thank her again.